I would now like to calculate the electric field of a dipole. That's a very simple one. This dipole consists of a positive charge, so we'll call this plus Q, Q positive, and a negative charge, this is minus Q. And these charges are separated by distance 2a. And now I'm going to pick a coordinate system with an origin in between the two dipoles. So we have O between these two charges. And I want to calculate the electric field at some point P. Now, P can be anywhere in space, so I'm going to give it Cartesian values of x and y. And I have I hat and j hat. And now I want to calculate the electric field associated with these two charges, which we know has a dipole moment. So here, I'm going to define a vector r plus. I'm going to define a vector r minus and a vector r to the field point. And here, I have a vector, let's call this with a p. And here, I have a vector from my origin to the charge plus. And here, I have a vector from the origin to the minus charge. And now, when we calculate our electric field, we have to write it out in terms of a linear combination of linear superposition principle. And so our field is k plus q times the vector. Now, this, we wrote it, remember our vector triangle, where r is equal to r plus r plus p. And so what we have here is this was the key vector in Coulomb's law. So we have the vector r minus r plus. That was cubed. And upstairs, it was r minus r plus. And that was the electric field associated with the positive charge. With the negative charge, it's minus q. And it's exactly the same type of result, r minus cubed over r minus, where we used a more compact way of applying Coulomb's law in a coordinate system. So our goals now, in order to analyze these terms, is first off to write out our three vectors. The vector r is x I hat plus y j hat. The vector r plus, now remember that's the vector from the origin to the positive charge. The whole distance is 2a, so that's only a distance a. And so that is a j hat. And the vector r minus is minus a j hat. And so we now have all of our terms defined. I'll just show one in particular, that this is when we subtract these two vectors, we have x I hat plus y minus a j hat. And there'll be a similar term for, we'll write it out just for this calculation, so you can see it very explicitly. This is minus minus, so we have a crucial plus sign there. And that's all we need, because we can take the magnitudes of those vectors by just squaring the components, square root. And we've now defined all the terms. It's a little bit messy. So we have the electric field at a field point, which I'm now going to indicate by its coordinates, x and y. And I'll write the two terms, one on top of the other, one line first. Down here, I have to square this. So I have x squared plus y minus a quantity squared to the 3/2 power. Again, the magnitude is to the 1/2, and we're cubing it. And upstairs, it's just x I hat plus y minus a j hat minus a very similar term for the other one, kq over x squared plus y plus a squared to the 3/2 times x I hat plus y plus a j hat. And that is our electric field no matter where the point P is located in space. The next question that we want to ask is, suppose that let's define r to be the distance from the origin to the point P. And let's suppose that r is much, much greater than a. Then how can we take this expression and look at its far field limit when we're very far away from the dipole, which has the dimension of a? And that will be our next task, is to figure out how to apply this in this special case. We calculated the electric field in Cartesian coordinates and for any point x and y. Now what I'd like to do is set up a calculation in which we look at the limit that the distance of the point P is much greater than the distance between the characteristic distance between these two charges. And what we'll do is we'll make an expansion, and the leading order term is something that we'll call the electric dipole field associated with these charge configuration. But before we do that, we have to rewrite our expression for the electric field in a manner in which we can start to make these expansions. So the first thing we want to look at is these denominators, which we'll rewrite in the following way. We'll write r plus p cubed, which is equal to this quantity, which is the distance from the positive charge to p. And what I'm going to do is first expand that, x squared. Now when I expand y minus a squared, I get y squared minus 2ya plus a squared. And that's all to the 3/2 power. And I'm going to pull out the r squared in here. And when I pull out the r squared, we'll rewrite that in the following way. R squared minus 2ya plus a squared to the 3/2. 2ya, there's an a in there. And now when I pull out the r squared, this is a little bit complicated because you're taking an r squared out, something that's to the 3/2 power. So first you'll take the square root, r, and then cube it. And so we get that r plus p cubed is r cubed times 1 minus, well, let's do plus, minus the quantity 2ya plus a squared over r squared, all to the 3/2 power. Now, what I'd like to do is, this is a complicated term. I'd just like to indicate it as 1 plus s plus to the 3/2, where s plus is equal to minus 2ya plus a squared over r squared. Now, when I look at r minus p cubed, that's this denominator here, which is the distance from the minus charge to the plus charge. Everything is exactly the same, except when I do the square here, instead of having a plus charge, a minus sign here, I'll have a plus sign. So that will be plus, plus, and I'll call this s minus. So I'll write this as r cubed times 1 plus s minus to the 3/2. And the only difference in this calculation is that s minus is plus 2ya plus a squared all over r squared. And that's the first step in setting up our expansions. But now what I'd like to do is I'd like to write my electric field as it's a vector field, so it has an x component function and a y component function. And I'd like to treat each of these component functions separately and get expressions for them. So let's start with the x component function. What I'm doing is I'm taking this first term component, subtracting from that. We see both terms have our constant kq. In the denominators, both of them have an r cubed. In both numerators, there is an x. And the only difference is the denominator here is 1 over 1 plus s plus to the 3 halves. And the other one is a minus 1 over 1 plus s minus to the 3 halves. And that's our x component. Now, the y component, it's very similar. We have the same kq over r cubed. What we have here, notice we have a y minus a minus y plus a, and the denominators will be similar to those expressions. So we have y minus a over 1 plus s plus to the 3 halves, negative, because the other charge is negative, y plus a over 1 plus s minus to the 3 halves. And this is, again, another way of rewriting this expression for the electric field in terms of its two component functions. But now that I have it set up in this way, I can now make a power series expansion of each of these quantities using the Taylor formula. And that's where we'll go next. We now want to consider our case where we're very far away from our source distribution. And what that means is, if we look carefully at these terms, s plus and s minus, notice that they go like a times a distance y, but this is at best 1 over r. And over here, it's a squared over r squared, so that goes like 1 over r squared. So in both of these cases, the quantity s plus and s minus, they are both very small. And that's what we're going to exploit in this expansion, because we have the result of applying the binomial theorem that this quantity is 1 minus 3 halves s plus. Now, the next term in here turns out to be 15 over 8 s plus squared, and that series goes on. But this is the term that we're going to ignore. And by ignoring that term, we can write out our expansion in the following way. We have that 1 over 1 plus s plus to the 3 halves is approximately 1 minus 3 halves s plus, and similarly 1 over 1 plus s minus to the 3 halves is approximately 1 minus 3 halves s minus. And now we can treat each of these terms separately in the expansion. And let's just work first with the x component. We have that factor kq over r cubed on the outside times a factor x. And now we're using both of these expansions. And so we have 1 minus 3 halves s plus minus 1 minus 3 halves s minus. And so you can see that the 1's cancel. We have the factor 3 half on the outside. And we can write that as minus 3 halves kq x r cubed times s plus, that's where the minus is, minus s minus. Now, when we look at s plus minus s minus, which we have over here, we can see that the a squared over r squared terms are canceling. And we just have these first terms, minus 2y over a r squared minus 2ya over r squared. So this becomes minus 3 halves kqx over r cubed. When we subtract these two terms, s plus minus s minus, we get a negative sign 4. So we have a minus 4 y a over another factor r squared. We're now approximating this, and so we get that ex xy, the two minus signs cancel, 6 k q xy a over r to the fifth. And in this particular problem, our magnitude of our dipole moment is 2aq, because it's a distance 2aq apart. So we could write that as 3kp xy over r to the fifth. Now, you might look at this and think the field is falling off like 1 over r to the 5, but that's not quite right, because x and y are at the location of the field points. They're on the same order as r to the fifth, so this is really showing us something that falls off like 1 over r cubed, which is not a surprise, because the whole distribution was neutral, so it shouldn't have a 1 over r squared term associated with point charges, but the leading order term is approximately goes like 1 over r cubed. Now, the other term, it's a little more complicated. So let's see what we can get. We have, again, kq over r cubed. We have, this is a little messier, 1 minus a times 1 minus 3/2 s plus. That's expanding the s plus term using our expansion. A minus sign, 1 plus a times 1 minus 3/2 s minus. Now, this one's a little bit trickier. Let's just look at some of the things that appear in here. We really have to expand these terms. And what we'll see is the y's are going to cancel. Maybe it's just a little bit wiser to expand all these terms out. We get y minus a. And over here, we have minus 3/2 y s plus. We have plus 3/2 a s plus minus y plus a. That's the first one. And the next one is y. There's a minus 3/2 s minus y. And finally, there is the term minus 3/2 a s minus. So this one was a little bit more complicated. And now what we want to do is just clean up that term. We'll need a little room over here to do that. So let's just get rid of those terms. We don't need them anymore. And now let's look carefully at what we have. The y's cancel. The minus a does not cancel. And we have an extra term in here. So what we get is that e y xy is kq over r cubed. We have a minus a and a minus a. So that's minus 2a. I'll just denote the terms that have canceled. Over here, we have minus 3/2 y s plus. And over here, we have minus 3/2 s minus y. So that looks like minus 3/2 times y times s plus minus s minus. And that takes care of those terms. And our last terms, we have 3/2 a s plus minus minus 3/2 a s minus. So we get a 3/2 a s plus plus s minus. Now, that was a little complicated. We've already seen that our s plus and s minus term, we have to now subtract these and add them. And so we get kq r cubed minus 2a. Now, when we subtracted those, there's a minus 2y over r squared minus minus 2y over r squared. That's a minus 4y over r squared. So we have minus 3/2 y times minus 4y a over r squared. And our last term is over here. That's plus 3/2 a. And when you add these together, these two terms cancel, and we get a factor of 2a squared over r squared. We're almost there. Now, what we want to look at is these terms. Notice we have a factor 2a, and over here we have a factor that goes like a cubed over r squared. So when we compare this one to that one, it is very small. We have to be careful with our, yeah, we're OK. So this term is much smaller than that term, which we can neglect. And so this term we're going to neglect because it's much smaller than the leading order term. And we have k cubed r cubed times minus 2a. Over here, we can write that as 6y squared a squared over r squared. And now, again, let's just check orders. Why didn't we throw this term away, a squared over r squared? But remember, y is the position of the field point. It can be on the same order as r squared. So we should have no factor a squared here. And that's a nice check, because these have the same order. This can't be right. And notice that I missed my factor. I added an extra a there. And so there's the result for the electric field. And there is the x component and the y component. These expressions are complicated. And next we'll look at how to think about those in a different coordinate system. Let's continue our calculation of the leading order contribution to the electric field when we're looking at a field point which is very far away from the source charges. Now, we calculated this in our last video, and we have the dipole moment, so we can rewrite that y component of the electric field in terms of the dipole moment p. That means we can get rid of our factor q. It's the dipole moment k, our constant p over r cubed. We have a 2a cubed, so there's a minus 1. There's a 2a in here times q, so we just have a 3y squared over r squared. And remember, in our result, r is equal to x squared plus y squared to the 1/2. And that's an expression for the x and y components of the electric field to leading order in our approximation. And this is what we call the dipole field. Now, our next step is we'd like to rewrite this in a traditional way using polar coordinates. So let me write a coordinate system again. We'll put plus q and minus q. Now, what's done traditionally is I'm going to introduce the vector r. And in polar coordinates in the plane, we have two angles r and theta. I can define them any way I want. We've often defined theta with respect to the positive x-axis, but in this case, I'm going to define theta with respect to the positive y-axis. And that's going to introduce r hat and theta hat. And our coordinate system now would show us that our y is adjacent to the angle. So it's r cosine theta. And our x here is opposite the angle. And so x is r sine theta. And so I can write the x component here in terms of polar coordinates. Notice x component, but the variables that we're describing the components, we still are using I hat and j hat here, are given by r and theta in the plane, and we have 3 kp. Now x is r sine theta, and y is r cosine theta over r to the 5th. And now you can see explicitly that this goes like r cubed because of the factors sine theta and cosine theta are numbers between 0 and 1. And so that really shows explicitly that the x component falls off like 1 over r cubed. And the y component, that already, well, we'll see the same effect. We have 1 minus 3, and here we have r squared cosine squared theta over r squared. And so we have this is equal to kp over r cubed times 1 minus 3 cosine squared theta. And that is our y and x components of the fields written in terms of the polar coordinates in the plane. What we haven't done yet is to re-express these in terms of the unit vectors r hat and theta hat, and that will be our last step. For our electric dipole field, when the distance r was much greater than the distance we had 2a between these two charges, and we introduce an angle theta, and because of that, we have our r hat and our theta hat directions. We've been expressing everything in terms of I hat and j hat, and so we have to be a little bit careful about some vector analysis here. This is the angle theta, and we have also that, therefore, this is the angle theta. And what we see is that if we expressed r hat, so if we call that I hat and called that j hat, then r hat has an adjacent component in the y direction, an opposite component in the x direction, so that's sine theta I hat plus cosine theta j hat. And our theta hat is, again, it has a negative component in the y direction and a positive component in the x direction. The x component is adjacent to the angle, and so we have our vector decomposition. And now we wrote down our electric field in terms of r and theta, and we had k times the dipole moment over r cubed. Again, in this problem, the dipole moment was 2qa. And in here, we had a factor 3 cosine theta sine theta. And over here, we had a factor 3 cosine squared theta minus 1. This was our I hat component. And this factor was our j hat component. Now, what I'd like to do is express everything in terms of r hat and theta hat. And the reason we want to do that is it's often a very convenient way to express the dipole field. And what we're going to do is play a few mathematical tricks here. First thing we'll do is write this r and theta, kp r cubed. And what I'm going to do is I'm going to write this as two terms. I'll have a 2 cosine theta sine theta I hat plus another term cosine theta sine theta I hat. And I'll have a second term, which I'm going to write as cosine squared theta minus 1 j hat. But I'm still missing a factor 2 in here. So I have a 2 cosine squared theta j hat. Okay, that looks a little bit complicated at first. And now I'm going to use the trig identity that cosine squared theta minus 1 is minus sine squared theta. And I can rewrite my expression for our field as kp over r cubed. And now I'm going to collect these factors. I'm going to pull out a cosine theta here, there, and a 2. So I have 2 cosine theta. I have sine theta I hat plus cosine theta j hat. Let's just click the terms off that we've used so far. And the second term is I'm going to pull out a sine theta. And I have cosine theta I hat. But remember, this is minus sine squared theta. I'm already pulling out a sine theta. So I have a minus sine theta j hat. And now let's express this in the following way. We have kp over r cubed. Our first term is 2 cosine theta, and that is precisely r hat. And our second term is plus sine theta, and here we have cosine theta minus sine theta, and that is theta hat. And finally, that is the expression for our electric dipole field in polar coordinates. Now remember, what precisely is this? This was the leading order contribution to the electric field when r is much bigger than a. And now we have a nice, concise expression entirely in polar coordinates.